In the deep silence between galaxies, there exists a number that does not glow or roar yet quietly governs everything that moves apart in the dark. A number without mass or shape yet heavy enough to carry the fate of the universe. It is written not on stone or star but into the stretching fabric of space itself. A measure of how fast the cosmos is expanding and how relentlessly distance is being borne from distance. This number is known as the Hubble Constant. It is not merely a rate but a cosmic tempo, a slow widening breath that began after the first light escaped the newborn universe. With every passing second it determines how quickly galaxies drift beyond reach, how light thins into red, and how the future opens into colder, emptier space. For decades this number was assumed to be knowable, singular, and calm. But now it refuses to settle. Measured one way it whispers one value, measured another it speaks a different truth. Observations of the early universe etched into the cosmic microwave background tell one story. Measurements of the nearby universe traced through exploding stars tell another. Both are precise, both are careful, both are correct within their own rules. Yet they do not agree. This disagreement is not small. It is not noise or error waiting to be smoothed away. It is a widening crack where certainty once lived. A tension that grows sharper with every new telescope, every refined dataset, every improved calibration. If the universe cannot agree with itself, then something fundamental is missing. Either an unseen force once shaped the early cosmos, or space and time behave in ways not yet written into equations, or the universe has been quietly evolving its rules while observers watched only the results. This is not simply a problem of numbers. It is a question of destiny, because within this single value lies the story of how the universe began, how it grows, and how it may one day end. And the question now hangs in the expanding dark. Is this the most important number in the universe? And is it trying to tell humanity that reality is far stranger than imagined? High above the smog and gaslight of early 20th century Los Angeles, a solitary mountain rose into the thin, clear air. At its summit, Mount Wilson Observatory waited in quiet patience, its great mirrors aimed toward a sky still poorly understood. Here the universe would begin to confess a secret it had carried since its birth. In the years following the First World War, astronomers believed the Milky Way was the whole of existence. The night sky appeared vast yet finite, a single island of stars surrounded by unknowable darkness. Faint smudges called nebulae drifted across photographic plates, their nature uncertain, perhaps clouds of gas, perhaps something stranger. Most believed they lay within the Milky Way, mere ornaments embedded in its spiral arms. Edwin Hubble arrived at Mount Wilson not as a revolutionary but as a careful observer. Armed with the Hooker telescope, then the most powerful optical instrument on Earth, he studied these nebulae with methodical precision. Night after night, glass plates captured faint spirals of light so distant their photons had traveled for millions of years before touching human instruments. Among these distant spirals, Hubble noticed stars that pulsed with rhythmic regularity. They brightened and dimmed in steady cycles like cosmic heartbeats. These were Cepheid variable stars, first studied by Henrietta Leavitt at Harvard College Observatory. Leavitt had discovered that the period of a Cepheid's pulsation was directly related to its true brightness. By comparing apparent brightness to intrinsic luminosity, astronomers could measure distance across vast cosmic scales. This was not guesswork. It was one of the first reliable cosmic yardsticks. And when Hubble applied it to the spiraling nebulae, something extraordinary emerged. The distances were too large. Far too large to fit within the Milky Way. These objects were not clouds within a single galaxy. They were galaxies themselves, entire star systems separated by unimaginable voids. The universe suddenly expanded in scope, becoming not a single city of stars but a sprawling cosmic archipelago. Yet the discovery did not end there. As distances grew clearer, another pattern revealed itself, quietly at first, then unmistakably. Spectra of these galaxies showed their light stretch toward the red. This redshift suggested motion not sideways but away. The farther a galaxy lay, the faster it appeared to be receding. This relationship had been hinted at earlier by Vesto-Slipher, whose measurements showed nebulae moving at tremendous speeds. But distance had remained elusive. Now Hubble brought velocity and distance together. Plot by plot, point by point, a straight line emerged. Distance on one axis, velocity on the other. The universe was not static. It was expanding. From this simple yet profound relationship, the Hubble constant was born. A proportional rule stating that the farther a galaxy lies, the faster it moves away. Not because galaxies are fleeing a central point, but because space itself is stretching, carrying galaxies along like leaves on a widening river. At first, the number was wildly uncertain. Hubble's early value was far too high, suggesting a universe younger than Earth itself. The error bars were enormous, the data sparse, the assumptions crude by modern standards. Cepheid calibrations were incomplete, interstellar dust dimmed light in subtle, deceptive ways. Even the nature of galaxies was still being debated. Yet the idea endured. As technology advanced, the numbers slowly sharpened. Astronomers refined distance ladders, correcting biases, identifying new standard candles. Type Ia supernovae emerged as powerful tools, explosions of white dwarf stars reaching nearly uniform peak brightness. Radio astronomy opened new windows, gravitational physics matured. Then in 1990, the Hubble Space Telescope rose above Earth's atmosphere. Free from atmospheric blur, it gazed deeper and more clearly than any optical telescope before. Its mission was not only to capture beauty, but to measure with unprecedented precision. To reduce uncertainty, to carve error bars thinner and thinner. Cepheid variables were observed in distant galaxies. Supernovae were calibrated with greater confidence. Distances stretched farther than ever before. And with each refinement, the Hubble constant settled closer to a stable value. What emerged was not merely a number, but a cornerstone. It fed directly into estimates of the universe's age, its size, its future. Combined with Einstein's general relativity, it shaped the standard cosmological model. It influenced how dark matter and dark energy were inferred. It helped transform cosmology from philosophy into precision science. For decades, this number appeared obedient, adjustable but converging, a value that seemed destined to stabilize as instruments improved. The universe appeared cooperative, yielding its expansion rate with quiet compliance. But beneath the calm surface, something unresolved lingered. Early measurements depended on local cosmic neighborhoods. Later measurements would look back toward the universe's infancy. And the assumption remained that the universe followed the same rules then as it does now. The Hubble constant became a bridge between epochs. A thread connecting the universe moments after the Big Bang to its present vastness. It assumed continuity, consistency, harmony. That assumption would later be challenged. But in this discovery phase, the universe had already undergone its first transformation. From static to dynamic. From singular to expanding. From timeless to evolving. A single number had changed humanity's place in existence. Revealing that space itself is not a passive stage but an active participant in cosmic history. What began as faint pulses on photographic plates had become one of the most important parameters in all of science. A number that would soon refuse to remain simple, and would begin to whisper that the universe still had more to say. For much of the late 20th century, cosmology entered what many believed was an age of confidence. The universe appeared measurable, charted, and increasingly obedient to theory. Satellites mapped the sky with exquisite clarity, telescopes refined distances to staggering precision. Equations once written in chalk now aligned with data collected from the edge of time. The cosmos seemed to agree with itself. Then the measurements began to separate. At first, the divergence was subtle, almost polite. A few kilometers per second per megaparsec difference here, a slight shift there. Numbers that could be blamed on dust calibration selection effects. The kind of disagreement science expects and patiently resolves. But the gap did not close. It widened. Modern measurements of the universe's expansion rate divided into two distinct camps, each built on radically different windows into cosmic history. Both precise, both careful, both grounded in decades of refinement. And yet both pointing to incompatible truths. One camp looks backward almost to the beginning, to a time when the universe was only 380,000 years old, still hot, dense, and opaque. Before stars, before galaxies, before darkness truly existed. When matter and radiation were locked together in a glowing plasma. As the universe cooled, light finally broke free. That ancient radiation still fills all of space today, stretched by expansion into microwaves. This relic glow is known as the cosmic microwave background. In the early 21st century, the European Space Agency's Planck satellite mapped this background with extraordinary sensitivity. Tiny temperature fluctuations, just millionths of a degree, revealed a snapshot of the infant universe. Not chaos but structure. Ripples that encoded information about geometry, matter, energy, and expansion. Using Einstein's general relativity and the standard cosmological model, these fluctuations could be decoded. From them, scientists inferred the universe's composition, its age, and its expansion history. The Hubble constant emerged indirectly from this ancient light. Not measured directly but calculated from initial conditions and physical laws. Planck's result was remarkably consistent internally. The early universe appeared calm, predictable, governed by equations that fit together with near perfection. The expansion rate it predicted was lower than many expected. About 67 kilometers per second per megaparsec. At nearly the same time, another camp was measuring the expansion of the universe not by looking back but by looking around. Into the relatively nearby cosmos where galaxies glitter and stars still burn. This late universe method builds upon the cosmic distance ladder. A layered approach where nearby distances calibrate farther ones. Parallax measurements anchor Cepheid variable stars. Cepheids calibrate type Ia supernovae. Supernovae illuminate galaxies across billions of light years. The Hubble Space Telescope played a central role here, observing Cepheids in distant galaxies with unprecedented clarity, reducing uncertainties, accounting for dust metallicity and bias. Later infrared observations further sharpened the picture. These measurements were not indirect. They were geometric, luminous, and local. They measured how fast galaxies are moving away now. And the number they found was consistently higher, around 73 kilometers per second per megaparsec. This was not a fluke. Independent teams using different telescopes, different datasets, and different analysis techniques reached the same conclusion. The universe nearby was expanding faster than the universe predicted from its earliest light. At first, the discrepancy was treated cautiously. Science expects friction between methods, especially when one peers across 13.8 billion years of cosmic evolution. But the tension refused to fade. Statistical significance grew. Error bars shrank. Confidence hardened. The difference crossed 5 standard deviations. The threshold physicists reserve for discovery. Too large to dismiss as chance. Too persistent to ignore. This disagreement violated a foundational assumption, that the universe evolves smoothly according to the same underlying laws from birth to present. If the early universe predicts one expansion rate and the late universe measures another, then something is deeply wrong. Either the early universe model is incomplete, or the late universe measurements hide an unknown systematic error, or the universe itself changed its behavior along the way. This conflict became known as the Hubble tension. The word tension is deceptively gentle. In reality, it signals stress on the foundations of modern cosmology. The standard model known as lambda CDM relies on 6 parameters tuned to remarkable precision. Dark energy represented by a cosmological constant. Cold dark matter shaping structure. Inflation smoothing the early universe. The Hubble constant ties all of these together. Change it and the balance shifts. The age of the universe changes. The growth of galaxies alters. The inferred properties of dark energy evolve. Precision cosmology depends on consistency. Independent measurements converging toward a single truth. The Hubble tension breaks that expectation. What makes it especially unsettling is that both sides are exquisitely careful. Planck's measurements are among the most precise in all of science. The distance ladder has been scrutinized for decades. Bias's dust evolution selection affects all tested and retested. New methods entered the scene. Gravitational lensing time delays. Tip of the red giant branch stars. Masers orbiting supermassive black holes. Even these tended to favor the higher expansion rate. The universe appeared to be arguing with itself. If the late universe is correct, then something altered expansion after the cosmic microwave background was emitted. Perhaps a brief phase of additional energy early on. Perhaps new particles influencing radiation density. Perhaps gravity behaving differently across scales. If the early universe is correct, then local measurements are systematically skewed. Yet no single error large enough has been convincingly identified. The discomfort deepens because cosmology had grown accustomed to success. The discovery of dark energy. The confirmation of inflationary predictions. The mapping of large-scale structure. Each victory reinforced confidence in the framework. The Hubble tension challenges that calm. It suggests the framework may be incomplete, not broken, but unfinished. Einstein himself once introduced the cosmological constant to force a static universe. Later he abandoned it, calling it his greatest mistake. Now a version of that constant dominates the universe's energy budget. History whispers caution. Cosmic numbers have misled before. This tension is not merely academic. It touches the deepest questions. How old is the universe really? How fast is it changing? What unseen components govern its fate? In the quiet gap between 67 and 73 lies the possibility of new physics. Or a reminder of humility. Precision has revealed paradox. And the universe once thought cooperative now stands distant, inscrutable. Expanding faster or slower depending on when and how it is asked. The Hubble constant no longer behaves as a simple ruler. It has become a fault line. And along that fault line modern cosmology now waits, listening for the sound of something deeper shifting beneath the equations. As the disagreement hardened into something undeniable, cosmology did what it has always done when confronted with uncertainty. Look closer. The hope was simple and deeply human. That somewhere along the long chain of measurement a subtle flaw waited to be uncovered. A miscalibration, a bias, a hidden assumption quietly bending the result. If found, the universe might return to agreement. If corrected, the numbers might finally converge. The first place astronomers turned was the foundation of the late universe measurements. Distance itself. Measuring distance in the cosmos is not a single act but a ladder built rung by rung. Each step depends on the strength of the one below it. And at the very base lies parallax. The tiny apparent shift of nearby stars as Earth moves around the Sun. For centuries, parallax was elusive, too small to measure reliably. But in 2013, the European Space Agency launched Gaia, a spacecraft not designed to photograph beauty but to measure position with extraordinary precision. Gaia's mission was ambitious: to map more than 1 billion stars in the Milky Way, to chart their distances, motions and motions again, to turn the galaxy into a three-dimensional atlas. With Gaia's data, parallax measurements reached unprecedented accuracy. Distances to nearby Cepheid variable stars once uncertain were now anchored with confidence. This allowed astronomers to recalibrate the entire distance ladder from the ground up. Cepheids themselves were studied anew. Their pulsations observed across multiple wavelengths. Their metallicity effects corrected. Their environments carefully analyzed. Infrared observations became crucial. Dust that dims and reddens visible light becomes nearly transparent in infrared. The Hubble Space Telescope and later the Spitzer Space Telescope observed Cepheids in infrared bands, reducing one of the largest sources of systematic error. Supernovae too underwent refinement. Type Ia supernovae, long treated as standard candles, were revealed to be more subtle. Their peak brightness correlates with how quickly they fade. Corrections were improved. Host galaxy properties accounted for. Samples grew larger, cleaner, more uniform. Statistical techniques advanced. Selection biases were modeled. Data pipelines were stress-tested. Independent teams cross-checked results. With each improvement, uncertainty shrank. And yet the expansion rate did not move toward the Planck value. It stayed stubbornly high. Meanwhile, the early universe measurements were scrutinized with equal intensity. The Planck satellite had mapped the cosmic microwave background with breathtaking resolution. Temperature variations across the sky measured to microkelvin precision. These tiny fluctuations correspond to density ripples present when the universe was less than 500,000 years old. Planck did not simply observe the universe. It performed a cosmic census. The size and spacing of the ripples revealed the geometry of space. Their amplitude encoded the amount of matter and radiation. Their distribution reflected the physics of inflation and the behavior of primordial plasma. From these patterns, cosmologists extracted parameters with astonishing precision: the age of the universe, the density of dark matter, the fraction of dark energy, and indirectly the Hubble constant. The inference depends on a web of physical assumptions: general relativity, standard particle physics, a cosmological constant that does not change over time. Within that framework, Planck's data fit together almost perfectly. Internal consistency was extraordinary. Residuals were minimal. Alternative fits offered little improvement. Small changes to the early universe parameters, however, can echo dramatically across billions of years. A slight increase in radiation density speeds up early expansion. This alters how sound waves propagate in the primordial plasma, which shifts the scale of features imprinted in the cosmic microwave background, which then changes the inferred expansion rate today. This sensitivity makes the early universe both powerful and fragile as a probe. A tiny new ingredient could reconcile the tension, but it must fit within all existing constraints. To test whether the disagreement was merely a clash of methods, astronomers sought independent approaches. Measurements that bypassed traditional distance ladders altogether. Gravitational lensing provided one such path. When a massive galaxy lies between Earth and a distant quasar, its gravity bends light, creating multiple images. Variations in the quasar's brightness arrive at different times along each path. The delay depends on the geometry of space and the expansion rate of the universe. By carefully modeling the lensing galaxy and measuring these time delays, astronomers can infer the Hubble constant. No Cepheids, no supernovae. These measurements consistently leaned toward the higher expansion rate. Another method focused on a quieter class of stars: red giant branch stars nearing the end of their lives. At a predictable point, they ignite helium in their cores, producing a sharp cutoff in brightness. This tip of the red giant branch serves as a standard candle distinct from Cepheids. Using this method, some measurements yielded slightly lower values, but not low enough to fully align with Planck, and still higher than expected if systematic error were the sole culprit. Even water masers orbiting supermassive black holes were enlisted. Their precise motions mapped by radio telescopes offer geometric distance measurements nearly free of astrophysical assumptions. These too tended to favor a faster expanding universe. Each new dataset arrived with anticipation. Each analysis carried the quiet hope of resolution. But the tension endured. What was once a disagreement between two methods became a pattern across many, a convergence toward disagreement. The more carefully the universe was measured, the less cooperative it appeared. This deepened the mystery. If independent techniques point in the same divergent direction, then the problem is unlikely to vanish through improved calibration alone. The possibility began to loom that the universe is not behaving as expected. That something beyond the standard model is subtly influencing expansion. Perhaps the early universe contained a brief episode of additional energy now gone. An early dark energy component that briefly accelerated expansion before fading. Such a phase could reconcile the early and late measurements without disrupting later cosmic history. Perhaps neutrinos behave differently than assumed, possessing additional species or masses that alter radiation density in the early universe. Perhaps gravity itself evolves, not violating Einstein's equations locally but diverging slightly on cosmic scales. Each proposal carries consequences. Each must fit within the tight lattice of existing observations. Large-scale structure, Big Bang nucleosynthesis, weak lensing, galaxy clustering. So far, no single explanation satisfies all constraints, but none have been ruled out entirely. The deeper investigation has not simplified the picture. It has sharpened it. Cosmology now stands in a rare and delicate moment, where precision exposes ignorance, where improved clarity reveals complexity rather than order. The Hubble constant, once thought to be a single calm number, now appears layered, dependent on epoch perspective, perhaps physics itself. The universe seems to be saying that measuring it more carefully does not always make it easier to understand. The tension remains, not as an error waiting to be fixed, but as a question growing louder with every answer. And in that unresolved space between measurement and meaning, modern cosmology continues its slow, careful listening, knowing that somewhere within this disagreement may lie the next transformation in humanity's understanding of reality. As the evidence accumulated, the tone within cosmology began to change. What had once felt like a technical disagreement now carried the weight of something more unsettling. The hope that a single overlooked error would dissolve the tension slowly faded. Systematic errors are the quiet ghosts of science. They hide not in randomness but in assumptions, in calibration choices, in environmental effects, in the subtle biases of instruments and methods. For years, cosmologists hunted these ghosts relentlessly. Cepheid distances were recalculated with Gaia. Dust corrections were refined with infrared data. Supernova samples were expanded, diversified, standardized. Selection effects were modeled and remodeled. On the early universe side, Planck's analysis pipelines were tested against alternative methods. Foreground contamination from our own galaxy was scrutinized. Beam systematics, detector noise, cosmological priors, all examined in detail. Independent teams repeated analyses from scratch. Different statistical frameworks were applied. Blind analyses were conducted where results were hidden until methodologies were locked. The result of this collective effort was not convergence but confidence. Confidence that the measurements were doing what they claimed to do. Confidence that the disagreement was not a mirage. As instruments improved, the error bars shrank. The numbers sharpened, and the gap remained. This persistence is what transformed unease into alarm. If uncertainty had been large, disagreement could hide within it. But precision leaves little room to escape. Cosmology had reached a point where both sides of the measurement were extraordinarily precise. Yet they described incompatible universes. At this stage, the tension could no longer be dismissed as an inconvenience. It became a challenge to the underlying framework itself. That framework is known as lambda CDM, the standard cosmological model, a compact set of assumptions that has guided understanding of the universe for decades. Lambda represents dark energy, a mysterious component driving the accelerated expansion of the universe. Cold dark matter represents an invisible scaffolding shaping galaxies and clusters. Together with ordinary matter radiation and the imprint of inflation, they form a model of remarkable predictive power. Lambda CDM explains the cosmic microwave background with stunning accuracy. It reproduces the large-scale structure of galaxies. It accounts for gravitational lensing. It predicts the abundance of light elements formed after the Big Bang. It has survived test after test, earning a reputation as one of the most successful models in the history of science. But its success comes with unease. Most of its content is unseen. Dark matter has never been directly detected. Dark energy is defined more by its effect than its nature. Inflation remains a hypothesis supported by indirect evidence. Lambda CDM works, but it does not explain everything it invokes. The Hubble tension presses directly against this model. Because within lambda CDM, the expansion history of the universe is tightly constrained. If the early universe predicts one expansion rate, then the late universe must follow from it. There is little freedom to diverge. And yet the divergence is observed. This suggests that either one set of measurements is wrong, or the model connecting them is incomplete. As systematic explanations grew less plausible, attention shifted toward new physics. Not reckless speculation but cautious extensions grounded in known principles. One possibility is that the early universe contained an additional component of energy. Not dark energy as seen today, but an early dark energy phase. A brief injection of energy before recombination that altered expansion just enough to reconcile the measurements. Such a component would leave subtle fingerprints, shifting the sound horizon scale, altering the cosmic microwave background without destroying its overall agreement with observations. Models along these lines have been developed, tested, constrained. They ease the tension but often create new discrepancies elsewhere. Another possibility involves neutrinos. These ghostly particles are abundant and influential in the early universe. If additional relativistic species existed, or if neutrinos possess unexpected properties, they could modify early expansion. Again, the idea is plausible. Again, the constraints are tight. Others have looked toward gravity itself. Einstein's general relativity has passed every local test with precision. But cosmology probes gravity across unimaginable distances and times. Perhaps gravity behaves slightly differently on the largest scales. Modified gravity theories attempt to preserve local success while altering cosmic behavior. Many struggle to fit all observations simultaneously. The point is not that any one proposal has solved the problem, but that the problem demands such proposals be considered. This is the hallmark of a deep mystery, when established explanations no longer suffice, and the cost of ignoring the discrepancy grows greater than the risk of exploring beyond the known. The Hubble tension exerts pressure, not explosive but constant, like tectonic stress building beneath the surface of theory. Every new dataset adds weight. Every confirmation tightens the strain. Cosmology is not accustomed to this kind of conflict. The standard model of particle physics contains tensions and anomalies. But cosmology had entered an era of concordance, a sense that the broad picture was complete. Now that confidence is being tested. The discomfort is philosophical as much as technical. If the universe does not behave consistently across time, then the assumption of a single immutable set of laws may need revision, or at least expansion. History offers parallels. The precession of Mercury challenged Newtonian gravity. Blackbody radiation confounded classical physics. In each case, anomalies were not errors but clues. Einstein once said that problems cannot be solved at the same level of thinking that created them. The Hubble tension may be such a problem. It does not overthrow lambda CDM, but it strains it, suggesting that something essential is missing from the story. Perhaps a new field, a new particle, a new interaction, or a deeper understanding of time and expansion. The universe may be revealing its complexity not through dramatic explosions or exotic objects, but through a quiet disagreement between numbers, a reminder that nature often speaks softly, and that revolutions in understanding sometimes begin with a decimal point that refuses to align. The mystery deepens because there is no obvious escape, no simple correction waiting to be applied, no overlooked footnote to be amended. Instead, there is a growing sense that cosmology stands at the edge of another transition, where confidence gives way to curiosity, where success invites scrutiny. The Hubble constant once symbolized order, a clean proportionality linking distance and motion. Now it has become a question mark, a pressure point where the foundations of cosmology flex and groan, where the universe seems to ask whether humanity truly understands the rules it thought it had mastered. The disagreement persists, the model strains, and the mystery deepens, not with drama, but with patience, as the cosmos has always done. When established explanations strain under observation, science does not abandon discipline. It widens its imagination carefully, guided not by fantasy but by mathematics, consistency, and restraint. The Hubble tension has reached this stage, where theory begins to stretch beyond its most comfortable boundaries, not in desperation but in response to persistent evidence. Among the first ideas to gain serious attention is a subtle alteration to the universe's earliest moments, a proposal known as early dark energy. In the standard cosmological picture, dark energy emerges relatively late, dominating only after galaxies form when expansion accelerates. Before that, the universe is governed by radiation than matter, its behavior tightly constrained. Early dark energy proposes a brief deviation, a small additional component active only for a short time shortly before recombination. Not enough to dominate, but enough to slightly speed up expansion during a critical window. This acceleration would shrink the sound horizon. the distance sound waves could travel in the primordial plasma. That scale is imprinted in the cosmic microwave background and used as a ruler to infer the universe's expansion rate. If the ruler is smaller than assumed, then the inferred Hubble constant from early universe data would increase, moving closer to late universe measurements. Mathematically, this idea is elegant. Physically, it introduces a new scalar field that activates then fades, its energy density rising briefly then diluting rapidly, leaving little trace except its influence on expansion. Such models can reduce the tension, but not without cost. They often disrupt the fit to other observables: large-scale structure, weak gravitational lensing, galaxy clustering. The universe is unforgiving. Fixing one discrepancy often creates another. Another line of thought turns toward dark energy itself. The cosmological constant in lambda CDM is assumed to be constant, a fixed energy density per unit volume, unchanging as the universe expands. But nature rarely favors absolute simplicity. Dark energy evolves even slightly over time. If its equation of state deviates from a perfect constant, then expansion history changes. Models of dynamical dark energy introduce fields that roll slowly across cosmic time, altering expansion subtly, potentially reconciling early and late measurements. Observations constrain such behavior tightly, so tightly that only modest deviations are allowed. Still, even small changes can have large cumulative effects. Again, the models are intriguing. Again, they struggle to satisfy all constraints simultaneously. The early universe offers another possibility, one that involves not energy fields but particles. Neutrinos are among the most abundant particles in the cosmos. Nearly massless, nearly invisible, they stream freely through space, influencing expansion through their energy density. The standard model includes 3 neutrino species, but particle physics does not forbid more. Sterile neutrinos, additional relativistic particles, or other light degrees of freedom could exist. An increase in early radiation density would speed up expansion before recombination, altering the inferred Hubble constant. This idea fits naturally into existing physics frameworks and connects cosmology with laboratory particle experiments. Yet measurements of the cosmic microwave background and Big Bang nucleosynthesis tightly constrain such additions, leaving little room for dramatic effects. Even so, neutrinos remain a tantalizing frontier, ghosts that may still hide unexpected properties. As theories probe deeper, some turn toward gravity itself. Einstein's general relativity has endured a century of testing. From Mercury's orbit to gravitational waves, from black holes to cosmological expansion. But general relativity is tested most rigorously in strong fields and local environments. Cosmology asks it to operate across the entire universe. Modified gravity theories propose slight deviations on large scales, extensions rather than replacements, preserving local success while altering cosmic behavior. Some introduce additional fields. Others alter how gravity propagates. Many aim to explain cosmic acceleration without invoking dark energy. These theories can affect expansion history, structure growth, gravitational lensing. Yet, modified gravity models often face internal tension, matching one dataset while conflicting with another. Gravity appears stubbornly consistent, resistant to easy alteration. At the speculative edge lie ideas that stretch intuition further. Extra dimensions long theorized in high-energy physics could influence cosmic expansion. If space-time has hidden structure beyond 3 dimensions, its dynamics might subtly affect large-scale behavior. Other proposals consider evolving fundamental constants, quantities like the speed of light or gravitational coupling changing imperceptibly over cosmic time. Such ideas are provocative, but heavily constrained by observation, and often lack a compelling underlying mechanism. What unites all these theories is not their success but their restraint. None are embraced lightly. None are accepted without consequence. Each must fit into an intricate web of data. The cosmic microwave background, large-scale structure, supernovae, baryon acoustic oscillations, gravitational lensing. The universe demands consistency, and it offers no mercy for models that ignore it. The most striking aspect of the Hubble tension is not that solutions exist, but that none fully succeed. Each alleviates part of the discrepancy, at the expense of something else. This suggests that the solution may not lie in a single adjustment, but in a deeper rethinking. Perhaps the universe contains multiple subtle effects working together, each too small to notice alone, but together enough to shift expansion history. Or perhaps the assumption that the same physics governs all epochs must be revised, not abandoned, but refined. The history of science is shaped by such moments, where data outpaces theory, where confidence yields to curiosity. When Newtonian gravity faltered under Mercury's orbit, general relativity emerged. When classical physics failed to explain atomic spectra, quantum mechanics followed. These revolutions were not acts of rebellion, but responses to evidence. The Hubble tension may represent a similar threshold. Not yet a revolution, but a pressure building quietly. What makes this moment unusual is its subtlety. There is no dramatic anomaly, no explosion or singularity, only numbers, carefully measured, refusing to align. This refusal is meaningful. It suggests the universe is not broken, but incomplete in its description. Theories now circle the problem, not wildly, but patiently. Each hypothesis tested, each consequence traced, each inconsistency noted. The process is slow, deliberate, cinematic in its restraint. For now, no single theory stands victorious. None dissolves the tension without leaving scars. And that may be the point. The universe rarely reveals its secrets all at once. It invites persistence, humility, and imagination tempered by evidence. The Hubble constant remains a quiet ruler, but its silence now carries weight. A reminder that even the most successful theories are provisional, and that reality is under no obligation to conform to expectation. The mystery persists, not as failure, but as invitation, an opening toward physics not yet written, but patiently waiting to be discovered. As theory stretches and speculation circles the unresolved tension, science turns once more to its most trusted ally: measurement. When ideas multiply and certainty thins, instruments become arbiters, quiet judges that do not argue but observe. And in the unfolding story of the Hubble constant, a new generation of tools has begun to speak. At the forefront stands the James Webb Space Telescope, not merely a successor to Hubble but a transformation in capability. Its segmented mirror unfolds in the cold darkness far from Earth, its instruments tuned to infrared light where dust fades and distance clarifies. Webb does not simply see farther, it sees cleaner. Cepheid variable stars once veiled by interstellar dust now appear with unprecedented clarity, their pulsations measured across infrared wavelengths with reduced uncertainty. Subtle effects that once complicated calibration now stand exposed. Webb stability allows long, precise observations. Its sensitivity reaches Cepheids in galaxies far beyond Hubble's grasp, extending the distance ladder deeper into cosmic time. Type Ia supernovae 2 benefit. Infrared observations reduce scatter. Host galaxy effects are better constrained. Luminosities standardized with increasing confidence. The promise is not that Webb will magically resolve the Hubble tension, but that it will remove excuses. Systematic errors once suspected can be confirmed or dismissed. If the discrepancy remains under Webb's scrutiny, it will do so stripped of ambiguity. While Webb sharpens the nearby universe, other observatories prepare to map the cosmos at scale. In the high desert of Chile, the Vera C. Rubin Observatory nears completion. Its mirror and camera designed not for singular images but for motion and change. Night after night, it will scan the entire visible sky, building a time lapse of the universe in motion. This survey, known as the Legacy Survey of Space and Time, will catalog billions of galaxies, measure their shapes, distributions, and clustering, track supernovae by the millions. From this flood of data, cosmologists will extract patterns, Baryon acoustic oscillations imprinted as subtle ripples in galaxy spacing. Weak gravitational lensing tracing the invisible web of dark matter. These measurements provide independent constraints on cosmic expansion, anchoring geometry across vast distances, cross-checking the cosmic microwave background and distance ladder alike. Alongside Rubin, the European Space Agency's Euclid mission charts a complementary course. Orbiting far from Earth, Euclid maps the universe in optical and near-infrared. Its focus precise shapes distances and redshifts of galaxies across billions of light-years. Euclid is designed to probe dark energy directly, to measure how expansion has changed over cosmic history, to test whether acceleration behaves exactly as a cosmological constant predicts. Together, Rubin and Euclid will transform statistical cosmology, turning small samples into overwhelming populations, reducing cosmic variance, exposing subtle trends that smaller surveys could not reveal. Yet even these vast maps rely on light, and light can mislead. So cosmology turns to a radically different messenger, one that does not dim, scatter, or redden, one that travels through the universe almost untouched: gravitational waves. When massive objects collide, black holes, neutrons, stars, space-time itself vibrates. These ripples propagate outward, carrying information about their origin. The strength of the signal reveals distance directly. No calibration ladder required. When gravitational wave events are accompanied by electromagnetic counterparts, as in the case of neutron-star mergers, redshift can be measured independently. These events become standard sirens, cosmic beacons whose distance is known from physics alone. The first such measurement in 2017 provided only a rough estimate, but it proved the method viable. As detectors improve and event rates increase, standard sirens promise a new path to the Hubble Constant, one independent of Cepheids, supernovae, and the cosmic microwave background. Already future observatories are planned, ground-based detectors with greater sensitivity, space-based missions like LISA poised to listen to lower-frequency waves. Each detection adds a point to the cosmic ledger. Meanwhile, deep beneath Earth's surface, particle physicists probe conditions reminiscent of the early universe. Experiments studying neutrinos search for hidden properties, masses, mixing angles, potential sterile species, clues that could influence early expansion. Colliders explore physics beyond the standard model, looking for particles that might once have contributed to cosmic energy density. Axion searches, dark matter detectors, and precision measurements all converge, testing ideas that bridge the smallest scales with the largest. Cosmology and particle physics, once separate disciplines, now entwine, each informing the other, because the Hubble tension is not merely astronomical. It is fundamental. It touches space-time energy and the behavior of fields at the dawn of existence. What makes the coming decade extraordinary is the convergence of capability. Never before has humanity possessed so many independent probes of cosmic expansion, so many ways to ask the same question. Does the universe expand at one rate, or has its behavior changed across time? If new instruments converge toward one value, the tension may dissolve. The triumph of measurement. If they persist in disagreement, the implication is profound. New physics would no longer be optional. It would be required. Such a moment would echo across science, forcing revisions to textbooks, reframing cosmic history, opening doors to fields yet unknown. The universe has offered such moments before. When the expansion itself was discovered, when dark energy revealed its presence. Each time measurement led theory. The Hubble constant now stands at a similar threshold. The next decade will not answer every question, but it will narrow possibilities, expose inconsistencies, clarify what must change. The tools are ready. The data is coming. What remains is patience. Science does not rush revelation. It measures, listens, and somewhere within the quiet hum of detectors, the flicker of distant stars, the tremor of space-time itself, the universe continues to speak. Whether its message confirms established laws, or whispers of something entirely new, The instruments are poised, and the fate of a single number may soon reshape the understanding of everything that expands beneath the stars. In the end, the mystery returns not to equations or instruments but to meaning, to the quiet realization that a single number can illuminate the boundaries of human understanding. The Hubble constant was never meant to carry such weight. It began as a simple proportionality, a bridge between distance and motion, a way to describe how space stretches and galaxies drift apart. It was assumed to be measurable, finite, and final. Yet this one value now resists closure, refusing to settle into a single truth, refusing to be owned by one method or one era of the universe. In that resistance lies its power, because when a number refuses to agree, it exposes something deeper, not necessarily a flaw in nature, but a limit in description. For centuries, science has advanced by assuming consistency, that the laws governing the universe today also governed it yesterday, that equations written now apply across all of time, that reality is unified, stable, and obedient. This assumption has served humanity well. It allowed Newton to bind the heavens and earth with the same force. It allowed Maxwell to unite light and electricity. It allowed Einstein to weave space and time into a single fabric. But each advance began with discomfort, with data that refused to fit, with numbers that did not align. Einstein himself faced such a moment. Observations showed that Newton's gravity could not fully explain Mercury's orbit. A tiny deviation persisted, small enough to ignore, large enough to matter. Rather than dismiss it, Einstein followed the tension. He reimagined gravity not as a force but as geometry, space and time curved by mass and energy. From that leap came predictions that reshaped physics: gravitational lensing, time dilation, black holes. The universe did not change. Human understanding did. The Hubble tension carries a similar quiet insistence. Not dramatic, not catastrophic, but persistent. It does not announce a revolution. It invites one. It suggests that the universe may contain layers of behavior still uncharted. That expansion is not merely a passive stretching, but a process shaped by ingredients and interactions not yet fully known. Perhaps the early universe behaved differently than assumed. Not radically, but subtly, enough to echo across billions of years. Perhaps dark energy is not a constant presence, but a dynamic participant, evolving, whispering through cosmic time. Perhaps gravity itself wears different faces depending on scale. Faithful nearby, flexible across the vastness. Or perhaps multiple small effects conspire, each invisible alone, together shifting the cosmic story. These possibilities do not imply failure. They imply growth. Science is often imagined as a march toward certainty, but in practice it is a dialogue between expectation and observation, between theory and reality. When the two disagree, science does not collapse. It listens. The discomfort of unresolved tension is not a flaw in the process. It is its engine. The Hubble constant has become a mirror, reflecting not only the universe's expansion, but humanity's relationship with knowledge. It reveals how much has been learned, and how much remains uncertain. Cosmology has achieved extraordinary success, mapping the universe's history, measuring its age, tracing its structure, detecting its echoes. Yet even now the universe retains the right to surprise. This is not a sign of chaos, but of depth. Reality is not obligated to be simple, nor to yield all its secrets at once. The tension invites humility, a recognition that even the most precise measurements are interpretations, that models are stories told in the language of mathematics, useful, powerful, but provisional. It invites patience, because nature does not rush to reveal itself. It unfolds at its own pace, across generations of inquiry, and it invites wonder, because a universe that still resists full understanding is a universe still alive with mystery. The question of the Hubble constant is not merely about expansion. It is about trust. Trust in the continuity of physical law. Trust in the completeness of current theory. That trust is not broken. It is tested. And testing is how knowledge strengthens. The universe is not contradicting itself out of defiance. It is communicating through nuance, through the delicate difference between two precise answers. This difference may one day resolve, collapsing into a single value, explained by improved measurement or subtle correction. Or it may persist, demanding a new framework, a deeper synthesis. Their outcome enriches understanding. If the tension dissolves, it will affirm the resilience of existing theory and sharpen confidence. If it leads to new physics, it will expand the horizon of what is possible. In both cases, the journey matters, because science is not defined by certainty, but by curiosity disciplined by evidence. The Hubble tension stands as a reminder that the universe is not an object to be conquered, but a conversation to be continued. It does not shout its truths. It whispers them through faint light, through ancient radiation, through numbers that almost agree. In that almost lies the future of discovery. The universe is not broken. Its laws are not failing. Its structure is not unraveling. Instead, it is doing what it has always done, inviting deeper listening. As telescopes sharpen, as detectors grow sensitive, as theories evolve, the conversation continues. The answer may arrive quietly, or not at all, but the act of seeking reshapes understanding. A single number once thought settled now opens a door. Beyond it lies not confusion, but possibility, a reminder that the universe is larger than any equation, and that knowledge is not a destination, but a path, still unfolding, still expanding, like the cosmos itself.